Suppose I took some sort of material like styrofoam or something like that, and I hung it from an ideal string, and I charged it. Matter of fact, I had two of them that I charged what I'm hoping is somewhat equally. They're hanging with some angle theta here, or might be convenient to have this angle down here, but we have some angle theta and phi describing the orientation of this. And so I have some charge Q, call it Q1 and Q2. The distance from here to here is L. And the distance apart here, we'll call it D. And the question is, what are the charges? Well, if we look at the forces acting on Q1, do a force diagram here. I have tension pulling up this way. I have weight acting down this way. And then there's some electric force acting in that direction. It depends on if I want to do this in terms of theta or phi. Let's do it in terms of phi here. So we have Ft cosine of phi acting to the left, Ft sine phi acting up, mg acting down, and this electric force acting to the right, that way. It's an equilibrium as it's being held there. So I know that the electric force minus Ft cosine phi equals 0, mass times acceleration, but it's an equilibrium, so acceleration is 0. And we have Ft sine phi, and I guess let's set up a coordinate system here, I hat and j hat. So this is my I hat equation and my j hat equation. Ft sine phi minus mg equals 0. So Ft cosine of, I'll do sine first. Ft sine phi equals mg, and Ft cosine of phi is equal to Fe. If I divide both sides of the equation, I get the tangent of phi is equal to mg over the electric force, which is k q1 q2 over d squared. So this becomes d squared mg over k q1 q2. Now I can't identify necessarily if I have this lined up symmetrically. I know the force that's acting on each of these is going to be the same. When I charge them, it's going to be difficult to tell which one's Q1 and Q2. And so I will just assume Q1 equals Q2, which equals some generic charge Q. So this becomes d squared mg over kq squared. So solving for Q, I have Q squared is equal to d squared mg over k tan phi. And so Q would be the square root of mg d squared over k tan phi. Or consequently, if I know what the charges are, and let's suppose I'm trying to find Coulomb's constant here, or the electrostatic constant, I could just easily solve for k. So k would be d squared mg over q squared tan phi. If this was part of an experiment, I potentially could do a plot here. Let's see. So if I took whatever the material is in the ball here, I charged it up, and then I did my experiment, then my independent variable would be the charge on this. That's what I'm controlling directly. And then what I'm measuring would be the, well, either d or the angle. Matter of fact, we can get those in terms of the same thing. So let's explore that a little bit. So let's go back to our equation here, where I have tan phi is equal to d squared mg over kq squared. Looking at our triangle here, I know that if we have symmetry involved, that this would be 1/2 of d. So I have L and then 1/2 of d, and that's phi, and that's theta. I know that the cosine of phi would be d over 2L. This side over here would be the square root of L squared minus 1/4 d squared. And so the sine of phi would be the square root of L squared minus 1/4 d squared over L. Or the tangent of phi would be square root of L squared minus 1/4 d squared over 1/2 d. So tan phi is the square root of L squared minus 1/4 d squared over 1/2 d. Divided by that 1/2, the same as multiplying by 2, so I can multiply that 2 through there. And so that becomes the square root of 4L squared minus d squared over d is the tangent of phi. So back over here, we end up with the square root of 4L squared minus d squared over d is equal to d squared mg over kq squared. And so if d is our dependent variable, because how far they separate is dependent upon the charge on it, then I have 4L squared minus d squared over d cubed equals mg over k times 1 over q squared. Or depending upon how I want to do it, but I could treat that as my independent variable, that as my dependent variable. So I have 1 over q squared here, and then that there. And then my slope would be mg over k. If I know the mass of this, we'll just call that m1 and m2. If I know the mass of it, which is easy enough to do in an experiment, I just have an m here. I'll put subscripts on the diagram right there. So this just could be an average mass. So why don't we make that average mass? And so the slope becomes the average mass g over k, or k becomes the average mass g over the slope. And so we have an experimental way of finding Coulomb's constant. And that is probably going to be one of the experiments that you will be doing, or at least observing, or you get to watch the video of my doing it, depending upon how it works out.